value-added course. And then today topic is diversity technique in 5G and beyond. So this lecture will take by Dr. Abhijit Bhaumik. He is the professor in School of Electronics and Engineering, and he published lot of papers in the field of wireless and communication. So maybe you can get a very good knowledge in the diversity technique, how to solve the problem for the 5G and beyond. And apart from this, the sir has already shared some MATLAB program. So maybe if possible, you can open that MATLAB program and parallelly you can solve the problem. Now the session is hand over to the Dr. Abhijit Bhaumik. Okay.
Okay.
Okay, sir, continue.
Okay, thank you. Thank you for giving my well introduction, nice introductions. Today I'm going to take diversity. Since it is the second lecture already, that in the first lecture from first generation to fifth generation introduced by Dr. Maji. Today, I won't start directly to the diversity because there are a lot of students, those who are not, they don't have that communication background. They are coming from CS and other backgrounds also. So that's what I'll start. I'll start first. Just a minute. I'll start with a little introduction with the wireless, and thereafter slowly I'll move to the diversity. Let me share my PPT. Is it visible? Yogesh sir, is it visible?
Yes, yes. You can make full screen.
Just I'm sharing. Now?
Yeah, it's good.
Okay, fine. Okay. Is it changing? It's not changing, no?
No, sir.
No, no.
Just a minute. Yes, hello. Started. Now is it visible?
Visible, but slide is not changing. You just checked.
What is the problem? Okay, again I'm sharing. Stop sharing.
So maybe you can reshare or share the entire screen. So it is good. Share the entire screen.
Then in that case, I have to open the PPT, no?
Share the entire screen.
Okay, just a minute.
Just go to share. Then last option is entire screen.
Okay. Go to share. Then entire screen. Now it is it?
Yeah. Now it's good.
Bring. What
No,
is?
no. Just go to directly your PPT. Go to directly your PPT now. Go directly your PPT.
I can't see my PPT. Just a minute.
From downside, directly go to PPT. Yeah.
Just a minute.
PPT. Yeah.
Is it okay?
Yes.
Now is it visible?
Now you minimize this side one.
It's okay. Fine. Side one, no?
Yeah, minimize that one. No, minimize, not maximize. Once again, go to PPT. Yeah, it's okay. Yeah, good.
It's okay. Fine.
Yeah. Now you try to change. Yeah. Now changing.
Okay. Now it's changing, no?
Yes, correct.
Okay, fine. Welcome to this VSC, Next Generation Radio Communication. Today's topic is diversity technique. Uh, Before going to the diversity techniques, first I'll introduce a little bit about wired and wireless communication. Then I'll talk about what is the need of why the diversity is required. Then I'll discuss about several type of diversity techniques. At last, I'll take the spatial diversity techniques majorly. Thereafter, I will take one system model where we'll study about that all three spatial diversity techniques. Also, we'll run some MATLAB codes. Let us start with the word communication. You can see that word communication. This is basically this is okay. In a word communication, if you see, there is a transmitter and receiver. There is a transmitter and a receiver. There is a word connection between them. So it's a deterministic channel. This channel is deterministic. So, and it's a guided medium. That's what the received signal model. You can see y is equal to s plus n, where n is the AWJ noise and s is the transmitted signal. It may be a BPSK signal or a QPSK signal, depends on modulation type. So since there is no wireless, so there is no effect of fading. No effect of fading. There is a major advantage of wired communications. If you look at the BER, basically this is error probability. This is error probability. That is Q of under root of SNR. I'm not going to the detail of this, how it is derived. If you want to see, then I'll share the derivations, how we can this BER. Anyway, this is a Markov function Q, where this SNR is basically transmitting SNR, where you can see SNR is equal to P by sigma n square. P is the transmit power and sigma n square noise variance. If we take the same thing in parallelly for wireless communication, that's the received signal model becomes this one, where y is equal to hs plus n. H is basically now here is the wireless channel. It's a random in nature. It's a random in nature. It is also called fading coefficient. Okay, so if we compare the SNR here, SNR, if you look these two SNR, there is another term introduced since this wireless channel, H of square. This is a channel gain, where H is the link coefficient or channel coefficient. So obviously, the BER of the wireless channel becomes different. So instead of simple SNR, I have to replace this SNR by and H square into SNR. And this H square in some book may be denoted by A. A is basically this H square, mod of H square. This mod of H square is basically channel power. This is basically channel power. So in that case, error probability becomes Q into under root of A into SNR. Now look at here, both are error probability. And that if you look at the bottom figure, left side is all our wired communication, right side all our wireless communication. Once you have this error probability, how we can find the BER? BER is basically error probability. There's PV. There is an error probability by log 2M. M is the number of message constellations that depends on modulation technique. See, if I think about BPSK signal, there is M value is 2 because there are two message constellation only. One is +1, other one is -1. So two message points. If we think about a QPSK, then it becomes M is equal to 4. So this is how you can, if you have the error probability, you can easily calculate the BER of that particular transmission. Now come to the fading. When a signal, now I'm directly move to the wireless scenario, because already we compared the wired and wireless communications. If you look at the wireless communication, so obviously since this that term is already introduced, so due to that error probability will increase. And due to that BER also increase. So in case of wireless communication, BER of the network would be high as compared to the wired communication. Now move to the fading. When the signal is transmitted through a wireless channels, the signal has to face two type of fading. One is large scale fading, that is here large scale fading. Other one is a small scale fading. In large scale fading, large scale means basically when the signal travels from a transmitter to the receiver, it has to travel a distance, so it will has path loss as well as the shadowing effect. Shadowing means basically due to the obstructions and all, the signal fluctuates. Okay, due to that, the shadowing effects come. I'll show you in the equation of how we can describe the shadowing. So these two, basically path loss and shadowing, comes under the large scale fading. Whereas small scale fading, if we look at the small scale fading due to the temporal behavior, it's a temporal behavior. It's a short distance or within a short period of time, the variation in the channel. So if we look at this picture first, that path loss C is reducing exponentially, whereas shadowing is fluctuating. That is due to the that it indicates that that in the propagation path, whatever the obstructions are, they are not linear. They are non-linear. That's what this shadowing effects is fluctuating. Now here, if in this figure we incorporate both large scale and small scale fading, both fading are incorporated. If you see the deep black line, this is basically comes from the large scale fading. While these rate fluctuations, these are coming from the small scale fading. Why? For an example, why this is too fluctuating? See, if we consider for an example, say we consider a Wi-Fi signal. So it is transmitted at 2.4 gigahertz. That means its lambda is basically approximately 12.5 centimeter. Approximately, I cannot remember right now the exact value. Approximately 12.5 centimeter. So see, if we think about this scenario, there are multiple components are there. In the base station transmitting an information is that information or symbol reaches to the receiver. This is Rx, this is Tx. Reaches to the receiver through multiple paths. Now the problem is here. Say it is a zeroth position. Now suddenly the car moves to a distance. Say here, the distance is lambda by 2. That means lambda by 2 means approximately it is 6.25 centimeter. What happened? Say if the signal is at this peak, when that receiver is at this position, it is receiving this peak. Say all the signals it is receiving to the all multipath signal reaching to the receiver, all are constructive in nature. So we are getting peak. Once it is moved by lambda by 2 distance, means approximately 6.25. It's a very small distance. Then and there, what would happen? They become destructive and suddenly it will reach to here. The power level reach to here. Then again, if it moves another lambda by 2 distance, again it will may reach here. So you may find within a that you can imagine when a car is moving with a velocity, say 60-80 km per hour, 6.25 centimeter, how some seconds it will take, okay, or some milliseconds maybe. So within that short period time, that signal power fluctuates rapidly. So due to that, this fluctuation is coming. So this is basically this dynamic or random nature. Due to this random nature, the received signal power at the receiver fluctuates within a very rapidly within a short period of time or within a short distance. That's what the small scale, if you look at the small scale fading, is fluctuating too much. Now coming to the large scale fading, already I told, that is path loss and shadowing. When we consider the small scale fading, then little bit I'm moving to the deep little bit. What happened? Say this is a source, this is a basically receiver. So it has multipath. So the same signal traversing through the same different paths, hitting to the reflecting or diffracting from the different objects and reaching to the receiver. Since they are traveling different distances, so they will have their different reaching time. So means that means the same signal reach to the receiver at different time instant. So some of have say may have the same information, may have the different delays. One of them would be the very less delay. Say it is a maybe the line of sight path. It may take very short time. So I am indicated by tau short. Whereas this path or that path may be the longest path where the delay is maximum. So tau long is there. The time difference is basically delay spread. This is a very critical parameter in case of when you're describing the small scale fading. Now you consider the car starts moving. Once this car starts moving, obviously the Doppler shift effect comes. You heard about the Doppler shift when, just for an example, if you standing on a platform, if train reaching towards you and whistling, so as it was nearing to coming to near to you, that intensity of the sound is become higher and higher. That means the frequency of the signal is changing. So that is called Doppler shift. The same thing here. Once the car is moving, every multipath component will suffer from Doppler shift. That Doppler shift is defined by this FD term. F is equal to V by lambda cos theta. V is the velocity of the receiver. Lambda is the transmit signal, that is wavelength, and theta is the arrival angle. So from there, so since all the multipath components suffering from Doppler shift, one may have, nth component may have FD in Doppler shift, a zeroth path, that is maybe you can consider a lowest path, FD0, that difference is called Doppler spread. These two basically helps you to modeling the wireless channel. Now already talked about large scale, how you can model the wireless channels. One is that when you talk about path loss and all, there is a long distance path loss model. Simple, there is no shadowing, simple path loss, where D is the distance between transmitter and receiver. D0 is the reference distance. Normally used to consider 1 meter. And N is the path loss exponent. It depends on the environment. And this may be modified. When we consider the shadowing, this term will come. This is called, this entire model is called, and basically we have added this X sigma, that is a Gaussian distributed one, for include the shadowing effect with this path loss model. Then this model is called log normal shadowing model. Now, when we characterize what are the small scale models, there are several statistical models are there for wireless channels. One is Rayleigh, Bayesian, Nakagami. When we use the Rayleigh channel, when is a more severe fading, that is there is no line of sight path. If there is a line of sight, non-line of sight, both are there, but line of sight path is dominating. In that case, we use the Bayesian channel. Nakagami is flexible. It can be depends on that. AB is the fading parameter. Similarly, the Ryzen also has the fading parameter capital K. I will tell you later on. Once you change this M, that same Nakagami model can be act as a Rayleigh as well as the Ryzen. It's a more generalized model. See here, it is given here that Rayleigh, how we can, this is the Rayleigh distribution. This R is the envelope of the received signal, sigma square. Sigma square is the variance of variance. So this is how FRR of, that is how you can describe the Rayleigh distribution, and its CDF is there. Now, when you talk about the normalized envelope, then we'll replace this R by under root of 2 sigma square. If I do replace by A, the same equation, the FRR becomes this one. This is Rayleigh distribution, Rayleigh fading channel distribution, where H is the fading coefficient. Similarly, for the Ryzen distribution, the same becomes this one, A by sigma square. You can see the equation where that H here, this H is not, you may consider some other parameter, say some Z or something. You do not mix up with this H with the channel coefficient. this H. This is basically LOS component. LOS component. Okay, and I0 is the Bessel function. So when we are using the rise and fading, that LOS is path is dominant. Now this H, that LOS path, that is basically what is, I already told you what is the rise and fading parameter. That K is the rise and fading parameter that already mentioned. K is equal to basically LOS path component power by scattered path component power. Scattered path. Scattered means other multipaths. So this is basically this H square. This H means this one. This may be better. I could have used some other variable, but you should not use this H. It's my mistake. And this power scattered power is already mentioned here. It is coming from if you look at the variance of two random variable, if you take their variance, so one is sigma square, other one is also sigma square. So if you add them up, so automatically two sigma square will come. Anyway, then Nakagami distribution, I'm just briefly describing. I'm not going deep into this, all this, how it is coming, all this, just a brief introduction of these channels. Nakagami distribution is described where M is the fading parameter. Now see, just a minute. Now see here, when M is equal to 1, I can say, if I put M is equal to 1 here, it will behave like a Rayleigh channel. Just put M is equal to 1. So this value becomes, if you put M is equal to 1, this value becomes 1. This quantity become A, this become A minus A square, and here it is 2A square. So if you look at this, and this expression is same. So if I put M is equal to 1, the same Nakagami channel will behave as a Rayleigh channel. So there, this you can see the relation between M and K. It is already mentioned. That is if when K is equal to 0, if we put K 0, automatically M become 1. So it is a Rayleigh channel. When K is equal to infinity, M become infinity, then pure LOS, line of sight. Now, see, I'm moving to the deep fading. See, before going to the deep fading, already I mentioned what is channel Y is equal to H, X is the information or symbol, plus N. N is the noise, AWGN noise. See, this H is basically, this is the channel amplitude, and e to the power j theta. Theta is the that is angle of the channel. This is the channel amplitude. Now, if I want to, this is the basically signal part of the received signal, and this is the noise part. If I want to calculate what is the power of the signal part, this is the signal part, and this is the noise part. If we calculate the what is the signal power of the signal power, you can find it's basically expectation of mod of H into X square. That means it is basically H square and E of expectation of X square, and that equals to basically, say, it is P, the signal power P. So this is your signal power, and noise power is equal to E of N square. That is equal to sigma N square, noise variance. So this is my signal power. This is my noise power. When the signal power, received signal power, falls below the noise power, then deep fading occurs. Noise power means noise floor. So what is the definition of deep fading? When the received signal power falls below the noise floor or noise variance, then you can say the receiver is under deep fading. So if under deep fading, then what would happen? If under deep fading, then that means you won't be able to decode the information. The receiver won't be able to decode the information properly. So how we can address this differing probability? If we look at here, differing probability, so obviously from here, I can see from here, I can write this one because if we look at this, it would come like mod of h square less than sigma n square by p. And p by sigma n square already mentioned in the previous slide, that is SNR. Already mentioned, that is SNR. You see here, already mentioned that transmitting SNR. So I can write, so SNR, okay. So now, if we come here, thus the differing probability, what, how we can define the differing, what is the probability, that is PDF, differing probability, what is the probability that events occur, h square mod of h square less than 1 by SN. That event is called, that probability of this event is called differing probability. That means P of mod of h less than 1 by SNR, under root of SNR. Now, how we can define? That is how we can define. So that is basically 0 to 1 by under root of SNR f of h a into dA. And this distribution, if I take a Rayleigh distribution, 1 by under root of SNR 2a into to the power minus a square dA, I can get this expression. So this is the differing probability. So now you come to know what is differing. Differing means when your received signal power falls below or noise floor or noise variance. That means the receiver is in under differing. If it is under differing, then it won't be able to decode this information. So what is the remedy? How we can overcome from this differing? How we can combat this differing situation? So the solution is diversity techniques. Means what is the diversity technique? Diversity means basically you facilitate more number of channels to the between transmitter and receiver. Say for an example, say I have a transmitter this one, I have a transmitter this one, I have a receiver this one. If we have a single link, if due to the environment situations, randomness or whatever may be, if suddenly this goes under deep fade, the information carried by this channel link won't be decoded at the receiver. So you cannot decode the information. But if I create a situation like that, say if this is your transmitter and this is your receiver, instead of single link, if I provide multiple links, if one of them are deep-faded or all of them, at least there is a high chance, at least one link should be there, which is under good condition. Since they are carrying the same information, receiver can accept the information which is associated with the good link and decode its information. So I can overcome from this deep-fading problem. Okay, am I clear? So that's what in wireless communication, diversity technique are used to combat fading, shadowing, and interference by the sending and receiving same information through independent paths. These paths are independent from each other. Okay. Now, what are the types of diversity? One is time diversity, means basically that a channel is one, but you send the same information at different time instant. That is called time diversity. Frequency diversity means at the same time, you are sending the same information through different frequency bands. This is a frequency diversity. Another polarization diversity is there. In that case, polarization means you are basically, what is polarization? The signal propagation, say your signal is propagating in along the Z direction, but your the signal oscillation is different direction. How this signal oscillation, what is the angle of this signal, that is information oscillations, depending on that polarization is decided. It may be a horizontal vertical polarization, it may be horizontal polarization, maybe circular polarization. I'll come later on. Later on, that is a space diversity, very important, that is used in 5G and all as a very, I'll discuss more on that. Okay, where multiple antennas are placed in transmitter as well as in the receiver uh, to improve the link quality as well as the information rate. First, come to the time diversity. Time diversity. What is told? The time diversity transmits same information over different time instants, such that each copy experiences independent channel fading. Okay. In effective, that channel varies. Okay, fine. Here is the major information. Then delta t should be greater than tc. That is, tc is the coherence time. Tc is the coherence time. Very important parameter in wireless, coherence time. What is coherence time? The duration for which the channel remains static. Means during that TC period, the channel won't change. After TC, the channel will change. So you have to keep the channels. Means here I'm denoting the channel in terms of time. The link, if I think about from bandwidth point of view, the bandwidth is same path, just like a road. But I'm using a different instant. But the difference between two transmission instants should be greater than this TC. First, if it is less than, what would happen, I'll tell later. First, let us take, say, TC is equal to, for your understanding part, TC is equal to 5 milliseconds. My frame time or observation time is 20 milliseconds. So I can maximum create 20 by 5 less than 4 diversity channels. Here see, 0th millisecond, 5th millisecond, because my TC is 5 milliseconds. So I have to keep, because after 0, the first change in channel happens here. Then next at 10, then next 15, then 20. So that which was during 0th instant I'm transmitting, it will be treated as a H1. At 5th millisecond, it will be treated as a H2. At 10th millisecond, it will be treated as a H3, and at 50th millisecond, treated as a H4. Similarly, it is described, so I think you can understand. At 0th millisecond, H1, H2, T3, at H3, T4, H4. Because during this period, the channel remains static. After that, your channel will change. Here is another major important information. When I'm using this H1 at H1, H2, H3, I'm describing this channel with respect to time, H1, H2, H3, H4. I have to keep in mind one thing, this one, TS should not be greater than TC. TS should be less than TC. Why? Say if you start transmission here, since it is a TC period, if you extend your frame time up till here, so this portion of your signal frame will face channel change, because channel will change here. That means your frame is under fading. It would be a fast fading. So when we are deciding the channel instance, in that case, we have to keep in mind the symbol period also. So now the question may raise, if I keep delta t less than TC, what would happen? If I keep delta 2, means the time difference between the channels less than TC, because channel change after TC, this is the TC period. If I start this 0th time, if I consider H1, and after 4, say 1, 2, 3, 4, I'm considering this one as H2. Then since the channel remains static during this period, so the channel will be correlated to each other. Means that they will have same fading. See, but the main criteria of this diversity technique, the channels should be independent from each other. So this criteria is failing. That's what we cannot keep delta t less than Tc. So if I keep delta t less than Tc, they becomes highly correlated. So channel won't be independent from each other. Then the diversity, that features we cannot achieve. So we cannot overcome the deep fading problem. In case of time diversity, what is the received signal at ith instant? This is the received signal. If I combine the L, say if we have a L number of channels, if we combine them, so there will be a weighting factor, that is Wi. This would be conjugate of this channel. And what is the error probability? That is 1 by diversity value. So if you look at here, if you increase the L, PER will reduce. The error probability reduce, obviously. If L increases, PE will reduce. If PE reduce, BER also reduce. So what are the advantages here? No extra bandwidth, no extra antennas. These effective in wide bands, and it is used in CDMA wideband, ultra wideband. What are the disadvantages? Receiver design becomes complex. Sensitive to the channel estimation error. If there is any error, CSI means basically I talked about already H is equal to say HI. That is a H modus HI. Sorry. Okay, I'm writing it separately. H is equal to mod of H e to the power j theta. CSI, channel state information means what is the amplitude of the channel, what is the phase of the channel. If these two are estimated wrong, then maybe that decoding this would be wrong, this Wi would be wrong. Then in that case, you may not be able to decode the correctly that receives information. Now come to the frequency diversity. In case of frequency diversity, the same information is transmitted over the multiple frequency components. Here, that coherence bandwidth is introduced. Earlier it was a coherence channel, now it is a coherence bandwidth. What is coherence bandwidth? Coherence bandwidth is told here. Coherence bandwidth is the range of frequencies over which the channel response is almost the same. How could I understand? Let us take an example. Say I am transmitting a composite signal ST. It has two components, symbols, two informations. One is operating at say 1000 hertz. Another is operating at the 1005 hertz. And the obviously the signal bandwidth is 5 hertz. Now, see if the channel response, HF is the channel response. Normally, if any signal he wants to transmit, say what you use, X we have used, no, XT is transmitted, XT, it is transmitted, it passed through the channel impulse response is HF, HT, it is basically YT, convolution. So this, if I do the frequency domain response, I can get H of F, frequency response. So this HF is this one. If its response, say for both 1000 hertz and 1005 hertz is same too, just an example, it may be any other value, then I can say they are facing same response. They're getting, since they have for both the frequencies the same response for this duration, for this is the coherence, the bandwidth is coherence bandwidth. Okay, means both the signals are traveling through the coherence band of channel. But say when I'm putting, it is coming like for 1000, it is coming to the channel response, and once this 1005 hertz is passed through that channel, you are getting the response 0. They are not matching. That means these two frequencies suffering from different gains. That means that coherence bandwidth is less than that 5 hertz. So I think it is clear what is coherence bandwidth. The bandwidth, even that frequency channel that I mentioned, that channel frequencies, range of frequencies over which the channel response is almost same. For this case, that coherence bandwidth is 5 hertz, whereas for this case it is less than 5 hertz. Okay, And if you look at here, multiple these thousands and 5,000 in somewhere, if you read, it is maybe told as frequency components. Like these are the frequency components basically. Okay. Anyway, so now it is clear coherence band. So when we do the frequency diversity, we have to keep this difference of the band. We have to take different band. That band should be greater than BC, because till BC the response is same. So we have to keep the gap between two channel in terms of band that is greater than delay. If we keep delay less than BC, then they becomes highly correlated. Then diversity won't be achieved. How we can understand that? How in terms of frequency the channel, say my coherence bandwidth is 5 kilohertz. So I'll that F1, that 100 kilohertz, I'll use as a H1 channel. Then F2 I'll use as a 110. I can keep it is 106 also. Okay, just for the safety purpose, I kept it 110, then 120, 113. But I can't keep it. I can't keep. This is 100, 104. This is 108. I can't keep because it is less than 5 kilohertz. So for the safety purpose, that H1 channel, the same information X will be transmitted through this at 100 kilohertz. The same X will be transmitted through H2, that is 110 kilohertz. The same X will be transmitted through 120 kilohertz. The same will be transmitted through 130 kilohertz. So these are the four channels. This is the frequency diversity. Similarly, that what will be the received signal? It is mentioned here. What are the advantages? Strong mitigation of frequency selective fading. Okay, no need of multiple antennas over here, because we are basically exploiting the bands as a different channels, different bands. Highly effective in wideband system, robust against narrowband interference. It requires large bandwidth. Ineffective if the channel is flat faded, and higher receiver complexity. That is the problem. For both, whether it is a time diversity or frequency diversity, the receiver design is quite complex. Now polarizations. See here, polarization means, see here, the signal is propagating along this direction. The oscillation of the signal is this way, or that. This is called horizontal linear polarization. If the signal is propagating along this direction, but the signal oscillation is like this. This is vertical polarizations. The signal is propagating this direction. The oscillation is like this, circular. This is circular polarization. I can use the circular polarization as channel and transmit the same information to maintain the diversity. What are the advantages? Improved reliability without extra bandwidth, no additional time slots, useful for LOS or urban environment. Limited independence, polarization may be correlated, and sensitive to antenna orientation. Okay, if the antenna orientation change, it's a very important point. If the antenna orientation change, then polarizations diversity may face problem. So applications: 5G, 6G, bestest 4G, 5G, bestest satellite communication, MIMO system, millimeter wave systems. Now come to the space diversity. Space diversity means basically we are utilizing. We are going to utilize multiple antennas. How? First, I'll talk about the different possible cases. This is the transmitter. This is a receiver. This is the antennas. 1, 2, say L number of antennas. This X is transmitted, so I can transmit through this way. If I transmit, so there are L number of links are possible. L number of links are possible. Same X information, so H1, H2, HL. Same X information is passing through all the L number of paths and reaching to the receiver. This is called CMO. single in multi-out, CMOS system. It is called also receiver diversity. Receiver diversity. Another way we can do TX this is called meso system. Meso system. H1, H2, H3. This is called transmit diversity. But the problem of these two is it needs CSI, channel state information. Means after knowing the channel state information, then it precode and transmit. So transmitter's design is a little bit complex. Whereas in receiver diversity, there is no need of CSI. That is the advantage of CMOS. Another one is I'm not drawing all that, just I'm adding. Say it has 1, 2, up to T, 1, 2, up to R. So this is called MIMO. MIMO. So this is transmitter, this is receiver. Today we'll focus on CMOS system. CMOS. See, here, before that, see, okay, let me first draw the 1 second, that's CMOS 1. Sorry, I don't know where the eraser is available. Let me check. Okay, there. This antenna should not be here. This antenna should not be here because I'm talking about CMOS. Because I used it long back, I forgot the use, how to use that eraser and all. Up to L. So H1, H2, and HL. This is X. Okay. Now see here. Am I audible? Hello. When you talk about this CMOS, there is one transmitting antenna, multiple receiving antenna, the same information passing through the multiple channels. L number of channels are there because L number of antennas are placed at the receiver. One thing we have to keep in mind, the distance between two antennas should be greater than lambda by 2. Otherwise, the received signals become correlated. I have to make them independent. That received signal Y1, Y2, and YL, they should not be correlated to each other. So I can write Y1 here is equal to H1X plus n1, y2 is equal to h2x plus n2, yl is equal to dot dot yl is equal to hlx plus nl. Okay, fine. Now how I can combine them? Now that receiver has all L number of receivers, how I can combine them? There are three techniques available. One is selection combining. Selection combining. Combining, that is called S. In selection combining, what would happen? The receiver will select the best channel. First receiver, because the same information is passing through all the channels. One is heavily faded, one is moderately, one is very good. So out of N number of available channels, it will select the best one. Now how it can select? Based on their channel power. So how we can interpret them in mathematically? So basically that H, K, the K channel which is best one, that channel power would be the maximum of possible H1 square or H2 square or H square. Out of this all available channel power, which one is the best? It will select the channel. This is another way you can write. It's like K is equal to argument max of Hi, where I is equal to 1, 2, dot, 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 up to n. Means, sorry, this square, channel square. That means it will find for each I value, it will select which h of I square is maximum. Accordingly, that value of I will be stored at, will be given value of k. Then obviously, accordingly, you can find hk. So SNR in that case, SNR become P into mod of hk square by sigma square. This was selection diversity. So in selection diversity, what would happen? The receiver will select the best link and it will decode the associated information of that best link. This is the selection diversity. Next one is MRC, maximal ratio combining. Second one is maximal ratio combining. That is MRC. MRC and the next one I'll discuss EGC. MRC and the working of MRC and EGC almost same. Almost same. So I'll only draw the one figure. Then I'll discuss the both the techniques with the same model. TX RX here is W1, here is W2, and here is WL. The signal is transmitted. So it is H1, H2 up to HL. The received signals are Y1. Y1 is weighted with W1 by W1. Here it is Y2. Here it is YL. Then they are summed up, get Y. Y is a combined signal. This is for the MRC. So here Y1 is equal to H1X plus N1. Y2 is equal to H2X plus N2 dot YL is equal to HLX plus NL. So I can write it in terms of matrix. That is, if I write Y1, Y2 up to Y of L, then H1, H2 up to HL, then X plus N1, N2 into NL. So I can, for simplicity, I'm representing this matrix Y bar is equal to H bar into X plus N bar. That means Y bar is equal to this Y matrix. This Y bar is representing this matrix. H is representing this matrix. N is representing this matrix. Clear? Okay, fine. Now, what is Y? Y is basically Y is equal to, I can write W1 Y1 plus W2 Y2 plus Y WL YL. So I can rewrite in terms of matrix W1 W2 up to WL, then Y1 Y2 up to YL. So I can write, I'm writing it's a W Hermitian into Y bar. What is Hermitian? Before going that, say, if you have a matrix, real matrix, say, for an example, better I should say 1, 2, 3, 4, say A. So if I do the transpose, I'll get 1, 3. Okay. But say if A is equal to like this, 1 plus J plus J minus J, then 2 minus J. This is a complex matrix. In that case, instead of transpose, we have to use Hermitian. Hermitian means what? Hermitian means first find the transpose, then do the conjugate, or reverse. First finds the conjugate, then do the transpose. So if I do that, so if I follow any one of them, I'll get 1 minus J plus J, then minus J, 2 plus J. I'll get this. So if it is a complex number, instead of transpose, we have to follow Hermitian. So since my channel is complex, I've used Hermitian. Anyway, so if I use this WH, so Y bar is equal to, already have got this. So if I write H bar X plus N bar, I'll get W Hermitian H bar X plus W Hermitian N bar. Okay, so this is my signal part. This is my signal part, and this is my noise part. Right? Now I have to calculate what would be the SNR. That is my target, because SNR is the most important parameter to find the performance of any communication system. If you know the SNR, you can easily calculate what is the outage. You can calculate what would be the throughput. Throughput means data rate, that is silence per hour log to 1 plus SNR that you can use. So if I want to get the signal power, that is this one. So I move to the next slide. So signal power, I'll just do the one derivation. I'm not going to entire one, just for understanding purpose. So that is basically expectation of what was the signal? W Hermison, H bar into X. That is my signal power. I have to estimate. This is called expectation operator. So before coming there, I should define what is W Hermison. For MRC, the W is basically that weight I've defined already, W1, W2, WL. That is basically H1 by H norm, H2 by H norm, and HL by H norm. What is H norm? H norm is basically under root of mod of H1 square plus mod of H2 square plus dot HL square. So I think here, what is that W, that is called beam vectors, is also called. Okay. Here it is a weighting factor. Okay, fine. Now, so W Hermison, first I'll calculate what is this term. W Hermison, H bar, I'll find into X. So W Hermison means basically, if I can remember, H1 by norm of H, H2 Hermison norm of H, because W Hermison means what? W1, W2, that is, you have to get the this one up to WL. Okay, better I, okay, anyway. Then HL norm of H, and H is basically H1, H2 up to HL into X. So if I multiply them, what I will get? H1 square by norm of H plus H2 square by norm of H plus dot HL square by norm of H into X. So if I do them, mod of H square plus mod of H2 square, add them up, HL square by norm of H into X. From the definition, already I defined what is norm of H. Norm of H is equal to already defined under root of a mod of H square, H2 square, HL square. So from there I can write it's basically norm of H square by norm of H into x. So I can write norm of h into x. So my signal power become expectation of norm of h square. Oh, this should not be here. H square into x. That means, or better I should. Okay, I'm removing this. So this is equal to norm of h square into e of mod of x square. That is norm of h square into t. Similarly, if we try to noise term, that is W bar N bar, if I want to get that noise power, so noise power is equal to E of W, oh sorry, W Hermitian. I forgot to write the Hermitian here. Hermitian and N. Okay, what happened? N. So first I need to know what is W Hermitian N bar. That is equal to, again, W Hermitian means already we have got H1 asterisk by norm of H, H2 asterisk norm of H, HL, I forgot to mention asterisk, HL asterisk norm of H into N1, N2, NL. So here it becomes H1 asterisk into N1 by norm of H plus H2 asterisk into by norm of H plus dot dot HL asterisk norm of H. This would be the term. When I'm talking about the noise, so since I already mentioned that you have to maintain that distance between two antennas lambda by 2, the spacing, that's what it is called, spatial diversity. So these noises become independent from each other. So I can write E of N1 square is equal to E of N2 square is equal to E of NL square is equal to sigma n square. All the values same are considered. Okay. Whereas since they are independent, so N1 into say Ni into Nj become 0. So therefore, if I try to calculate this one, if I take the square of this term, so E of, if I take the square of this term, E of, so from here I can write, E of H1 N1 asterisk N1 by mod of norm of H plus H2 asterisk into norm of H plus dot dot HL asterisk NL by norm of H. So it is basically, I can write for each term. So it is better I should write like this. See, A plus B square means what? A square plus B square plus 2AB, like this. I'll get H1 h1 square by norm of h into E of n1 square plus, for this term I'll get, this is say a square, h2 asterisk square by E of n2 square, and so on. At the same time, I'll get some terms like h1, 2 into h1, h2, h norm square, E of n1 into n2. So this term of terms will come. So these terms, since the already I mentioned they are independent, they become zero. These terms become zero. Only the square terms will remain here. For each term, this is sigma n square, sigma n square, sigma n square. This is also sigma n square. So like all L number of terms, if you have a say a square, a two terms, a plus b whole square, you will have two square terms, b square. This 2ab, this is 0 basically. Two, if there is a successor, two terms are the square. Since you have a L number of terms, I'll get like this, like L number of terms, square terms. So if we, since all these are sigma n square, so I can write it as h1 square, and one thing keep in mind, h1 square mod of h1 square and asterisk square both are same, because say if I say h1 is equal to a plus jb and h asterisk would be a minus jb, when I'm talking about mod square, that means I'm talking about their amplitude. That means mod of h1 is equal to under root of a square plus b square. Similarly for it, asterisk square h1, that means again it is a square plus b square. So they become same whether it is asterisk or, so norm of h square, sorry I forgot to mention square here, all these terms should be square. Okay, norm of h square plus h2 square by norm of h square plus L number of terms, then sigma n square will come, because sigma square will be common from all. Then I can write it as, if I do the square, that h1 square plus h2 square plus h up to hl square by norm of h square, it will give you norm of h square of numerator. Denominator also give you norm of h square into sigma n square. So it will cross, so you will get only sigma n square. So what is the SNR for MRC? The SNR becomes, SNR for MRC becomes P into norm of h square by sigma n square. If we look at here, this is the signal power and this is the noise power. This can be written as more simple way. It is P of, you can write mod of h square as per your understanding, HL square. This is one way you can represent, or there's another representation, 1 to L hi square by sigma n square. So this is the SNR for MRC technique. So once you know the SNR, automatically you can calculate BER. BER is equal to, already found for VPS control, Q of under root of SN. So you put SNR MRC, you can get the BER. If you know the SNR, you can calculate what is the capacity of the link. B log 2, Shannon capacity 1 plus SNR MRC. So you can calculate BER, you can calculate capacity of the link. Okay, fine. Now, when you're talking about another diversity, which same working principle as MRC, that is EGC. Only the difference is the weighting factor values. This W. this W is changed. Rest operation is same. So here for EDC technique, the W is basically 1 by root L H1 by mod of H1. Instead of norm H, here it is, we use the H1 by mod of H1. H2 by mod of H2. Similarly, HL by mod of HL. If we use this and using the same method, how that MRC is derived, the SNR equation, the signal power becomes P into HI, I is equal to 1 to L square by L, and noise power become same sigma n square. So SNR for EGC technique, it becomes P I is equal to 1 to L H of I square by L into sigma n square. So if you look at these two SNR, this from the MRC, this is from EGC. So obviously SNR from MRC, SNR for MRC always greater than SNR for EGC. And if you compare all three diversity, spatial diversity technique, the performance selection company, that EGC is better than selection combining, and MRC is better than EGC. So MRC is best. We'll see in the simulation. So before going to the simulation, we'll create that system model for cognitive radio communication. Cognitive radio communication means 5G technology. What is that? Where that secondary users, basically there are two type of users. One is primary user, other is the secondary users. The secondary users basically suffering from channel congestions because band is limited. So what they will do, they look for the primary band. If the primary band is available, then it will transmit. The secondary user will transmit through the primary band. So before transmission, secondary users has to sense the channel, that is called spectrum sensing, and the technique is called cognitive radio technology, where it senses the signal which is available in the channel. That signal is denoted by, say, yi is equal to, if it is a noise only, there are two hypotheses, H0 and H1. If noise only, then yi is equal to ni, and if it is signal is also available, hi, si plus ni. There is a H1 hypothesis. Then it will calculate its energy. If the energy, it will be compared at with some threshold lambda. If it finds the wi, if wi is greater than lambda, then it would be decided H1. If wi is less than lambda, it would be decided as H0. If at some point wi is equal to lambda, then decision would be random. Decision would be random. That means it may goes under H1 or it may goes under H0. So what are the performance, sensing performance? How we can describe the sensing performance? One is false alarm. Under H0 condition, if you receive signal greater than lambda, means basically H0 means only noise you are receiving. Signal is not there, but still you receive signal power is greater than lambda. That means it is the system is telling user is there, but in reality, since it is a H0 means user is not there. Hypothesis is basically tells the true story, actual reality. H0 means user is absent. PU, primary user absent. Whereas H1 means PU, primary user is present. So under H0 means actually user is not there, but still the receiver is that secondary user is getting that WK is greater than lambda. That means user is there. That is called false alarm. PD under H1 condition means user is there. It is getting okay. That receive energy is greater than lambda. That is PD. Another parameter that is a misdetection. It is called 1 minus PD. Okay. So if I want to averaging them, so I have to that PD or I have to integrate PD over that 0 to infinity, considering that channel distribution. So I can get the average PDF. Anyway, I'm not going there. Now see, if we look at this here, basically H0, user is not there, but you are getting your transmitter or the device is getting its signal is greater than lambda, that probability of PF. So what is the probability the channel is actually when observation is channel is free, that is 1 minus PF. That is basically observation by the user when the channel is actually free. Observation is also that is user is not there and it is under H0 condition. That means here you are getting probability of W less than lambda and under H0 condition. This is the actual good true situation where the transmitter can transmit data. There will be no collision and the data will reach at the receiver safely. Now I'll take, because I'll run this simulation model. I have 2 programs I already given you. So that's what this system, that is a network model, is created. So you can understand the diversity with respect to a 5G network scenario. So that's what that cognitive radio relation network considered. Now this is the frame time. See, sensing already considered, sensing time. This is tau s, and this is transmission time. Once the sensing is over, it gets the channel is free, means 1 minus, it is observed that 1 minus PF here, then it will start transmission. So the total frame time T is equal to tau s plus tau r. So how we can formulate throughput? Throughput is basically total frame time minus sensing time. Total frame, so that is, this is basically my transmission time. This is basically my transmission time. So this is total frame time TA, this is sensing tau. So this TR is the transmission time by total frame. So this is the normalized transmission time. This is the normalized transmission time into C0 capacity of the link under H0 condition. That is what is the probability of H0 condition into 1 minus P. This is the throughput equation. So we'll run the simulations with this scenario. I'm going to that. I hope all of you have got the this both the programs. First, I'll show that. Okay. I'll show. I think is it visible? My screen is visible.
Yes, yes, yes.
Yes, sir. It is visible, sir.
So now I'm running that MATLAB window is there. Is it okay? MATLAB window. Hello.
Yes, sir. It is okay, sir. It is okay, sir.
MATLAB, no? MATLAB command,
yes, sir.
no? Okay. Yes, sir. So this is basically throughput analysis. If you look at the program, we have taken L is equal to 2, means 2 number of links are there. SNR is varying from minus 10 to 15 dB. And iterations, since it is a simulation, we have taken 20,000 simulations, multi-kernel simulations. TAP's transmission time is taken 100 milliseconds. Sensing time is kept 10 milliseconds. Okay. So normalized time, that using that formula TF minus tau by TF, I've considered. What is the probability of H0 condition? 0.7. PF is right now it is fixed. Next program it will change 0.1. Then we have investigated 3 SC case where maximum, see here, maximum channel power is selected. Maximum channel power is selected based on this channel. SNR is calculated, gamma SC. then link capacity is calculated. Similarly, for MRC, that is, if you can remember, that is P by sigma, that same Eisenhower equation we derived. Okay. Then capacity, that is by L, this same one is used. If I run this, you can find, just a minute. You can find, I think this is visible, that maximal, if you look at these three, maximal is combining as a better performance for a given SNR, achievable throughput is higher. If you see, if the average SNR increases, the throughput of the system increases, is fine. For a given SNR, if I use all three techniques, the maximal ratio technique outperforms of rest 2, equilibrium combining and selection combining. Now, see, if I what I do, increase the number of diversity path, L is equal to 4. If I make it L is equal to 4, what would happen? Let us check. Let us check. So whenever we run, we have to keep in mind this close all should be off, and whenever run the program, because we have to keep all the plots, so hold all should be there. So if I run it, you can find already this, I think result is obtained. You can find that if I increase the diversity path, whether it's a SC, EDC or MRC, the throughput for given SNR increases. So it means if you increase the more number of antenna, your system performance will improve. Second, I will take, in this program, I kept the sensing time fixed. Now, if I vary the sensing time with the fixed SNR, then what would happen? We'll check. So see here, I take TF frame time is kept 100 millisecond. Now tau, the sensing time is varying from 0.01 millisecond to 3 millisecond. 3 millisecond. We have taken 50 points, and FS is kept 6 megahertz, because basically whenever this cognitive video concept came, it was it was for the 3 megahertz band. So that's what the signal sampling frequency is kept 6 megahertz. If I run it, you can find just a minute. Before that, you can see if you look at here, that since the sensing time changes, automatically it would impact PF, false alarm. So that's what simulated false alarm created. PFs would be different. Then capacity for, I have taken only MRC here, because for the previously I saw that MRC is the best. So MRC capacity is checked here. You can look for the MRC, found the capacity. Just a minute. Then throughput equation, if we see the throughput equation, time ratio, that time ratio is TF minus tau by TF, 1 minus PF, PH0, the same formulation that used in the PPT, that is same. If you look at here, if the sensing time increases, throughput decreases. Why? Because if the sensing time increases, the transmission time will reduce. That's what throughput is decreasing. If I now say throughput is reducing, so how we can combat? Okay, what I can do, what is the possibility? I increase the number of diversity branches. Instead of B, I'm using some circle. Now I run it. Let's see what happened. Just a minute. It may take some time because it's a simulation. It may take done. You can find throughput improved. Once I used that L number of, so initially it was from 5 within 5 or 5.1. Now it is more than 5.8 bits per second per hertz. So you can see the improvement. So if you are getting less throughput, there is another way. Just increase the number of antennas at the receiver. Automatically, you can get higher throughput. That's all for today. Hello.
Any doubt?
Any doubt? If you have any doubt, you just write in chat. Yogesh sir?
Yes, yes, they can write. You can give some 2 or 3 minutes if they have doubt, so they can ask in chat or raise the hand. Okay, please.
I don't think they have any question.
You first stop sharing.
Hmm.
Yeah. Anything, please. So if you don't have any doubts, yeah, okay. So if you don't have any doubts, so we can close this session. Then thank you very much for Dr. Abhijit for giving the very nice presentation and complete detailed explanation about the diversity. So hope so you understand a lot of things from this particular lecture. Okay. So in the next class, that is on next Tuesday, 19th. Okay.
This is
So, oh,
celebration.
sorry, Thursday, not Tuesday. That is Thursday. Again, the 7:30, same link we can use. And the Dr. Abhijit Bhaumik will take the topic of resource allocation in D2D communication. Okay. So, thank you very much.
Okay. Shall I close?
Yeah,
Okay. Thank you.
Thank you, sir.
thank you. Thank you very much.